Okay, I'm going to be presenting a joint work with my student Karissa Sanchez and colleague Kristen Syrett. This is in fact Carissa's MA thesis work, and really she should be presenting it, but she could not make it. Okay, so let me set up our puzzle. We know that common nouns like fork or ball or shoe, they're some of the first words that children learn. They appear in infancy, in fact. And yet, late into the preschool years, children do something kind of odd with these nouns. When you ask them to count or quantify objects falling under these nouns, children don't distinguish between whole objects and discrete object parts. This behavior was first noted in work by Shipley and Shepperson in the early 90s, and they showed kids an array like the one on the left here with the forks, and asked them how many forks are there. And children said 6 over half of the time, counting not just the whole forks, but each individual fork part as one unit. In a different type of task, kids were shown an array like the one on the right and asked, who has more shoes, right? And 75% of the time, they said that the person with one shoe cut into 3 pieces had more shoes than the person with 2 whole shoes. And kids are doing this even though they understand that the discrete parts are broken or otherwise imperfect. So why are they doing this? One recent line of explanation takes this overcounting business to be a problem of noun understanding. These proposals start from the observation that even for adults, these count nouns can be used to talk about parts in select circumstances, like in the context of an archaeological dig. But the problem with kids is that they're overly flexible. They unselectively apply nouns to discrete parts and then subsequently overcount them. There are different explanations for why kids are overpermissive. So Mahesh Srinivasan and colleagues have argued that it's because kids can't immediately think of better ways to talk about discrete object parts like fork piece. My co-author, Kristen Syrett, and I have argued in earlier work that it's because kids are not as sensitive as adults to the contextual information telling you when to limit application to whole objects only. But these specifics aside, this categorization story makes certain testable predictions. So whatever the reason, children should allow for more things to fall under the count noun than adults. Second, how you count under a noun should depend on how you categorize. So if a fork piece is categorized as a fork, then you count it as one fork. If it's not categorized as a fork, then you exclude it from your counts. Yeah? But one can imagine a different possibility where the problem has nothing to do with nouns or objects, but with the ability to measure non-trivial things like object parts. So if we're being really precise here, these partial objects count for fractional shares. A half fork might not be one fork, but it is certainly more than none. But kids at this age may lack the capacity to reason over fractions. So they may recognize that a half fork puts the fork amount over 0, but the only way they can add it to a sum of forks is as 1. So this hypothesis has never been explicitly put forth in the partial object counting literature, but there is evidence from the number cognition literature that kids struggle with fractional concepts till fairly late. For instance, even 6-year-olds don't fully understand that there can be numbers in between integers. And the ability to do addition and subtraction with fractions tend to lag behind children's ability to do arithmetic over whole numbers. So if children's overcounting problem is a problem of non-adult measurement concepts, then that makes distinct predictions from the categorization story that we saw before. We might, for example, expect children to have generalized difficulties with words like half or 1.5, but more relevantly, we wouldn't be surprised if judgments of counts are independent of categorization. So our goal here was to test the predictions of these accounts. And we do this in a 2-task study where we look both at categorization and counting. And the counts involve not just whole numbers, but also a mixed number, 1.5. And throughout, we're going to compare behavior on nouns with gradable adjectives. So an adjective is gradable if it can hold of entities to greater or lesser degrees. So, we can say, for instance, that A is taller or older or more wealthy than B. Contrast this with non-gradable adjectives. So it's odd to say something like A is more married than B. Yeah? And we're going to focus on two varieties of gradable adjectives, maximum standard adjectives and minimum standard adjectives. And we chose these because they have clear and very distinct criteria for when something can fall under them. Okay. For an object to fall under a max adjective, it has to have the adjectival property to the maximal degree. Okay. So full is a classic example here. For a cup to count as full, it has to be completely full. A 3/4 full cup is not full. In contrast, min adjectives apply to anything that has at least some amount of the relevant adjectival property. So for an adjective like stripe to apply, something just needs to have at least one stripe. So here, both of these objects would count as striped. Now, if we imagine a parallel scale for a noun like ball, and we put these partial objects on it, how would that scale work? Right? Does the noun work more like max adjectives, where only the maximal element, the whole object here, falls under it? Or does it work more like min adjectives, where anything with some degree of ballhood could in principle fall under ball? And this is what we tried to establish in our first task in the design. So here, participants were given sets of 7 objects that exhibited some property in varying degrees. At degree 1, the object did not have the property at all, and at degree 7, it had it to a maximal extent. And then they were asked to put the balls, or the full ones, or the striped ones in one location, and the other ones in a different location, thereby creating a partition between category members and non-category members. So let me walk you through what we found. The x-axis here represents the 7 sequential degrees, and on the y-axis I'm plotting the rates at which an object was classified as a category member. So I should note that degree 2, at which point the object starts to display some amount of the property, that's going to be a region of interest for us because that's where min and max adjectives start to diverge. The object should already be a category member with min, but not with max. And the question is where nominals will fall. Okay. So for our adults, nominals, that's the green line here, starts to diverge from both the min adjectives and the max adjectives already at degree 2. But when we look across the degrees, it's clear that the overall shape of the line looks more like the max adjectives. In both cases, an object has to exhibit the property pretty close to the maximal degree to be reliably treated as a category member. For kids, in contrast, nominals pattern more like min. And at degree 2, we find no difference between the two categories in how often the object is classified as a category member. We do observe that at later non-maximal stages, acceptance increases for min, but the rates for nominals stay about the same, so we do get some differences. Okay. So in task 1, we see one locus of child-adult difference. Adults categorize nominals more like max adjectives, though with a bit more flexibility. Only whole objects or nearly whole objects were thought to fall under the noun, but kids categorize nominals more like min. So long as the object had some degree of nounness, it could fall under the noun for them. So this pattern is predicted on the categorization account. But notice that it's also compatible with the measurement account, which doesn't make any claims about how objects are categorized. Okay. Turning now to our task 2, this task looked at participants' judgments of counts. So after they finished categorizing the objects, participants saw object dyads from task 1 for each category, where one object displayed the property partially at the halfway point and the other displayed it maximally. And then they had to evaluate a puppet statement about how many x's there were, where the numerosity could be 1, 1.5, or 2. So in this case, the puppet might say, you brought me 1 striped one, or 1.5 striped ones, or 2 striped ones. And the participant had to say whether the puppet is right. Starting again with adults, here we're plotting rates of accepting the puppet's counts as correct. With max and min adjectives, adults behave as expected. They overwhelmingly accepted counts of 1 for max adjectives and rejected 2. They accepted 2 for min and rejected 1. They rejected counts of 1.5 for both adjectives, which also makes sense. A half full object is not full, and a half striped object is just striped. Okay? For nominals, participants accepted counts of 1, but they also accepted 1.5, but they rejected counts of 2, suggesting that for them, the partial whole dyad did not count as 2 n's. Here are the kids. So with adjectives, kids basically patterned with the adults, just a bit noisier, but their judgments for nominals were very different. They reliably rejected counts of 1 and accepted counts of 2. In fact, the acceptance rate for 2 with nominals was as high as that with minimum standard adjectives. And unlike adults, kids did not distinguish between the categories in their treatment of 1.5, which was pretty much uniformly below chance. So here we see some further differences between adults and kids. Adults count partial objects using fractional measures or not at all. Kids don't distinguish partial and whole objects in how they are counted. Adults accept the measure of 1.5 with nouns, but children just generally don't like it, probably signaling a lack of understanding of the expression. Now, both accounts can find some support in these results. Children's overcounting is predicted by both accounts. The specific difficulties with 1.5 is arguably predicted by the measurement account, but it's also compatible with categorization account, which doesn't say anything about these mixed numbers. So finally, we get to the critical question. Does categorization drive counting behavior as predicted on the categorization account? Or is counting behavior independent of categorization, which would be more in line with the measurement account? So to answer that, we first look at how this degree 4 partial object was categorized in task 1, and then look at how it figured into the counts in task 2. So in task 1, adults who are on the left here tended to reject the partial object from the category, though around 30% of the time it was categorized as a member. For kids, the pattern was flipped. So all this blue on the right is showing us that mostly the object was accepted into the category, though a bit over a quarter of the time, it was rejected. Now, the adults who rejected the partial object from the category, they rarely accepted counts of 2 for this dyad. Right? They're almost always ready to accept 1, but they also often accepted 1.5. So already we have a bit of a divergence between categorization and counts, facilitated by adults being able to access this more granular measurement scale and count halves. Adults who accepted the partial object as a category member, they were still not quite ready to accept counts of 2, though the acceptance rates here was higher. 1.5, though, is the preferred measure for this group. Turning to kids, when kids classify the partial object as a category member, their numerical judgments are pretty consistent. They tended to accept counts of 2 and reject 1. But what about when they rejected the object from the category in task 1? Here, the categorization story predicts a sharp drop in this group's propensity to accept counts of 2. But that's not what we find. Even children who rejected the partial object from the category tended to accept counts of 2. Right? Acceptance rates for 2 were in fact higher than either of the other 2 measures. Okay. So for both groups, count judgments pull apart from categorization. Adults are hesitant to count a partial object for 1 even after categorizing it as an X. Kids count the partial object for 1 even after saying it's not an X. So this discrepancy between categorization and counts is only compatible with the measurement account, which posits that adults have and children lack finer-grained ways to measure parts. So where does this leave us? Well, there's something to be said about the over-permissive categorization story. Children are indeed more accepting of partial objects into the category than adults. But that doesn't seem to be what's driving overcounting. The overcounting patterns can be well accommodated under the measurement account. Children seem to see that the cardinality of the partial whole dyad is greater than 1 in some sense, but without a better way of counting fractional shares, everything in between 1 and 2 get mapped to 2. So let me wrap by going back to the overcounting phenomena we started with and say what this proposal would mean for these earlier results. So a child presented with arrays like these may very well recognize that each broken piece constitutes some amount. They may recognize that the pieces can fit together and form a whole fork or a whole shoe. Still, they might not know proportionally what the fractional share of each piece is, and that's critical for counting. An adult understands that the 3 shoe pieces on the right here each count for 1/3 and sum up to at most 1 shoe. But it's precisely this type of numerical representations that we're proposing children lack. Thank you.
All right, we have time for some questions. Oh, over there.
Thank you, very interesting talk. I was just having a very curious question while you were talking about the objects. Do you know if there is any differences if you use food items? Because like for instance, banana or fruits, like they're more often exposed to half of them.
Yes, they're more food stuff is more sort of massifiable, so you can sort of count food, apple stuff or banana stuff as opposed to individual bananas. I don't know what they would do. So none of the studies that look at this phenomena have looked at food stuff, I don't think. Mostly they focus on artifacts, but that's an interesting direction. I don't have firm expectations about where they would go, but the measurement story would make a straightforward prediction because that is independent of objecthood, right? The inability to sort of count up fractions, one could totally take that into the mass domain and can be independent of count nouns.
All right, any more questions? Yuri?
Just a quick question about whether the function of the object interferes if the division results in one potentially functional member and the other is not.
Absolutely for adults, not obviously for children. So adults in our task, when they accepted a partial object into the category, they often sort of examined the object and said things like, I guess this bottle could contain some liquid. But children might spontaneously make those observations, and more often than not, they just said, oh, this can't really hold water. Okay, that's the bottle. So the functionality, it's not that kids don't recognize it, but that seems to be not directly tracking their counting behavior.
All right, nice question over there.
Whether something is the same, so one way to say whether something is the same object might be, for adults, might be to check whether the same object advantage exists. I was wondering if there's some equivalent measure we can use with children to see if they're actually completing the 2 parts differently, and that's why they actually have 2 objects rather than them lacking a partial concept.
Yes, I think I understand what you're saying, but let me clarify. So what you're observing, I think, is that adults have a kind of modalized notion of these fork pieces as being part of one imagined whole, right? But and this is sort of affecting how they count. And there is data showing that indeed when adults count this, they sort of count 5, which is not possible unless you're sort of fusing these pieces together, right? And you're pointing out that maybe children don't have that expectation that these fork pieces really fit together to form a whole. Yes. It's a possibility. I don't think that this has been tested.
Okay.
Okay, maybe 1 or 2 more questions. I think there's a student. Can you raise your hand? Okay.
Hi, very interesting talk. It's more of a clarification question, I guess. Do you, or how much are you implying that if you don't study fractions, you won't be able to solve this task. So how much is this related to, schooling in that story?
It's a good question, and I don't really know. So of course, at the time, I mean, based on what I know of the fraction acquisition literature, which is not as big as one might imagine, most of these concepts seem to come in kind of late into elementary school, and teaching fractions seem to be notoriously hard, but I'm not sure if that's really the fraction notation where sort of one's understanding of whole numbers really interfere, right? 1/4 is smaller than 1/2, but 4 is bigger than 2, right? And whether it's because of some conceptual change that is happening during those years. There are people, Rochelle Gelman in the 90s argued that there is really a conceptual change that happens sometime in elementary school, but people sort of debate whether or not that's necessary. I don't really know how much this requires schooling or whether this is something that matures as the child ages.
Okay, I think we have one last question in the audience.
Like when do like kids start like understanding like that half isn't a whole object?
Great question. So even kids who were in this, who were doing this study, who were 4 and 5-year-olds, they seem to have some understanding of the word half, but maybe not a number-like understanding of the word half. So they think that half might mean something like broken, right? It's a great question when they understand that half is, right, 1 divided by 2. Not sure. I would imagine that around 6 or 7, right, as some of these people have argued. Great question.
Okay, thank you for the questions. Let's thank our speaker.